Okay, so we left off where we talked about just our properties of multiplication. So we went through those again, keeping track of that we can't just flip-flop with our commutative property that we've had for regular multiplication of numbers. All right, we have something called the identity matrix. The identity matrix is basically where we have ones along a diagonal. So you can see here that these are all ones, everything else is zero. And when I multiply something by the identity, that's going to give me back my original matrix. So if I had multiplication of numbers, so if I have the number 3 and I want to multiply it by something and get 3, we know that that just has to be 1. So our identity for multiplication of numbers is just 1. For our identity for our matrices, basically this diagonal of 1s is going to perform an operation where we just get the same matrix back. And if you work through an example, you'd see pretty quickly why that's happening. All right. We're going to now talk about an inverse. And so an inverse is something that when I multiply on both sides, so when I have A times A inverse and A inverse times A, I'm left with the identity. And so this is the same kind of concept that we've had before. If I had 3 times x equals 9, the way we've solved that in the past is to multiply by the inverse of multiplication, which is division. So 1/3 times 3 is going to give me the identity for multiplication, which is 1 times x. And I just have to do that to both sides, and I would get our value. So we've done this before just with numbers, and now we're going to look at it using our matrix operations. All right, so the way that we can do that is we can verify, right? So if we basically multiply these two together, we should get the identity. If we do it both ways, we should come up with that diagonal of 1s and 0s. And so there's A times B, again, going row times column. So if we look at what for a 2x2 matrix, I would do row times column, which produces this value here, which turns into a 1. And if I go through the mechanics for all of those rows and columns, we get at the end our identity matrix. And so then we just have to verify that B times A also produces the identity matrix, and then we've shown that they are inverses. When we do that, we get the same thing. So that since we can do a left multiplication and a right multiplication and get the inverse, that turns out to, get the identity, it shows that those are inverses of each other. Now, if we have them, if we can verify them, that's fine. But if we don't have it, so you're going to, at this point, you've been given some possible choices. So you're going to pause the video here, and you're going to figure out which of these, when I multiply on the left and the right, give me the identity. So go ahead and pause the video, find your assignment sheet, and work through the guided practice problem for example 4. All right. So that was just verifying an identity, and if we've been given something, that's not too bad, but oftentimes we're not going to be given an inverse. We need to be able to actually find it. So if we're going to find an inverse, we're going to look specifically at how we find it by hand for a 2x2 matrix, and then show you how to use your graphing calculator to find the inverse when it's a larger matrix, such as a 3x3. And so what we're going to do is look at something called the determinant. So if I have a 2x2 matrix, I have such as A, B, C, D, and I want to know if this value of AD minus CB, so if I do the diagonals, so if I look at my diagonals, so AD and CB, and if I subtract them, if that's not equal to 0, then I'm going to have an inverse available. We'll say that it's invertible. And that value is called our determinant. Right? And so we can find our inverse by taking 1 over the determinant and multiplying that times all our values in our matrix. So let's look at an example of how that works. All right, so I want to find the determinant of this value. So I have a 2x2 matrix, and then use that to find the inverse. So again, for a determinant, I'm going to look at this kind of cross multiplication idea. I'm going to take those values, -5 times -8, and I'm going to subtract 4 times 10. And if that's not 0, I'm going to have an inverse that I could find. So when we look at that, I get my values there. And so this is not going to be invertible. I don't have an inverse because I have a determinant of 0. Right? If we look at another example, again, I have a 2 by 2 matrix, and I'm going to find the determinant. I'm going to take -2 times 6 and then 4 times -4 and see what we get. And so once we do that, I find that I get a 4. Since that's not 0, my inverse is going to exist, and I do 1 over the determinant times the 2 by 2 matrix to find our inverse. Right? So it's going to be invertible. I apply that value, and then I'm going to find the inverse. All I do is I take 1 over my determinant, so 1 over 4, and then I do scalar multiplication and multiply that times everything in there. So 1/4 of 6 is 3/2, 1/4 of -4 is -1, 1/4 of 4 is 1, 1/4 of -2 is -1/2, and that becomes my inverse. If I was to take this matrix and multiply it on both sides by my original matrix, I should get the identity matrix coming back. That's what it means for it to be an inverse. All right, so again, you're going to pause the video here and you're going to go back to your sheet and you're going to fill in the example 6 solutions as well as the guided practice for this value. So again, you're going to find the determinant using your cross multiplication. If that's non-zero, you're then going to be able to do a scalar multiplication and solve that value.